Billions of years ago, Earth looked nothing like the world we know. The skies were strange, the oceans red, and life was only beginning to take its first breath. Tonight we'll explore the forgotten Proterozoic Earth, a planet both alien and familiar. If you enjoy this journey, please like, subscribe and share, and tell us in the comments, what would you do if you could visit this ancient world? Thank you for watching. Now let's begin. In the long arc of deep time, the Proterozoic begins as Earth steadies itself after nearly 2 billion years of turbulence. The planet's surface, once a molten ocean of magma, now hardens into a crust thick enough to bear continents. The violence of constant bombardment fades, though occasional impacts still scar the cooling world. The air remains heavy and dim, a blanket of carbon dioxide, methane and nitrogen that filters sunlight into a copper haze. Beneath that sky, oceans stretch wide and shallow, no longer the acidic pools of earlier eras but calmer expanses, where minerals drift down to form the first stable seafloors. The global heat declines, though the core still stirs with energy driving convection currents that begin to push and fold the crust into vast shifting plates. On land, little moves. The continents are barren, grey and silent, their surfaces covered in volcanic rock and dust. Rain falls in steady cycles, carrying dissolved minerals back into the oceans, where they react with elements released from the mantle. Each droplet wears down the land a little more, returning the raw materials of the crust to the sea. The process is slow but relentless, a circulation that will define much of Earth's later stability. Under this early weather, a thin skin of clay and sand begins to form, hinting at the soils that will one day cradle plants. In the water, chemistry dominates over life. The oceans teem with molecules of iron and sulfur, carbon and hydrogen, all suspended in a delicate balance. Hydrothermal vents along mid-ocean ridges release minerals that feed chemical reactions at the base of the sea. The heat from these vents rises through dark water, curling and cooling in plumes. Around them, microbial communities thrive, tiny simple cells that feed on chemical energy rather than sunlight. These organisms have no eyes, no awareness, but they alter their surroundings molecule by molecule, releasing gases that drift upward toward the surface. At the boundary between ocean and air, another transformation begins. Sunlight, faint and scattered through the hazy atmosphere, penetrates the upper layers of water. Some microbes carrying pigments sensitive to light begin to harness that energy. They split water molecules to extract hydrogen, releasing oxygen as a byproduct. It is a process so subtle that it goes unnoticed by the planet itself, yet it marks a turning point in planetary history. Over millions of years, the faint trickle of oxygen accumulates, reacting with iron in the water to form rust-coloured sediments. The oceans turn murky and red bands of iron oxide settle across the seafloor, forming the foundations of what will later be seen as banded iron formations. Above, the atmosphere starts to shift. The dense haze of methane and carbon dioxide begins to thin, its chemical balance slowly altered by the new oxygen. The planet's colour changes, its skies taking on hints of blue, its horizon brightening. But the change is uneven and fragile. For long stretches of time, volcanic eruptions replenish the air with carbon gases, undoing some of the gains made by the photosynthetic microbes. Yet on average, oxygen continues to rise. The air once suffocating edges toward a composition that can sustain complex chemistry and eventually complex life. The continents themselves are no longer static. The mantle beneath them moves in slow, convective loops, pushing the plates together and apart. Where they meet, mountain ranges rise. Where they separate, new ocean basins form. the Proterozoic Earth becomes a planet of drifting masses, each carrying fragments of crust that will later assemble into supercontinents. The slow movement of land reshapes weather patterns, redistributes heat, and alters the composition of the oceans. Continental collisions thrust up volcanoes that pour out ash and gases, feeding both the air and the sea with new materials. The cycle of creation and erosion becomes continuous a rhythm that will endure for billions of years. As the surface stabilizes, the deep interior remains restless. In the mantle, hot plumes of rock rise and cool, transferring heat from the core outward. This movement powers the slow drift of continents and maintains the magnetic field that shields the planet from solar radiation. Without that invisible barrier, much of Earth's atmosphere would be stripped away. The field's strength fluctuates its poles, wandering unpredictably, but it remains one of the planet's enduring protections. In these early ages, auroras may already flicker at the poles, faint arcs of light shimmering through a thick alien sky. The planet's rotation, once rapid, begins to slow as the moon's gravity tugs on its oceans. Tidal friction gradually lengthens the day, adding minutes with each passing million years. This subtle change affects the cycles of temperature and light, shaping the rhythm of the early biosphere. The sun, slightly dimmer than it is now, delivers less energy to the surface, yet the greenhouse gases in the air trap enough heat to keep the oceans liquid. It is a delicate balance, one that could easily have tipped toward freezing or overheating. The Proterozoic world endures in a narrow window of stability, its conditions just suitable for the slow unfolding of biological and geological evolution. Life, though microscopic, begins to alter the world on a planetary scale. Cyanobacteria spread across shallow seas, forming mats that trap sediment and build layered structures known as stromatolites. These formations, rising from tidal flats and lagoons, are among the first large-scale evidence of organized life. Each layer records a cycle of growth microbes rising toward light sediment settling, and new cells growing atop the old. Over time, these layers become stone, preserving the rhythms of ancient ecosystems that will one day turn to fossil. The spread of these microbial mats accelerates the production of oxygen, which in turn alters the chemistry of the oceans and atmosphere. The balance between oxygen producers and consumers shifts repeatedly, creating intervals of stagnation followed by bursts of change. The planet's crust records these fluctuations in alternating layers of red and grey sediment, each marking a pulse in the slow oxygenation of Earth. The Great Oxidation Event, though far ahead in full expression, has its foundations in these quiet, shallow waters. Beneath this calm surface, the deeper Earth remains a crucible of change. Volcanic arcs rim the continents, spewing gases and molten rock. Tectonic boundaries slide and grind, generating earthquakes and reshaping coastlines. These processes recycle carbon between the atmosphere and the crust, linking the deep Earth to the surface biosphere. The interplay between fire and water, gas and rock sets the stage for the long Proterozoic transformation, a balance between planetary heat and the emerging regulation of life. By the close of this first stage, Earth stands poised between two eras behind it, the violent instability of the Archean. Ahead, the long and measured evolution of a stable planet. The oceans glimmer faintly under a dim sun. The continents, vast and barren, rest in slow motion, drifting across an ocean planet, now breathing its first quiet breaths of oxygen. The world has entered a calmer rhythm, one that will last for billions of years. Out of that stability, the next steps of complexity will rise, though for now the planet sleeps under the hum of its magnetic field and the whisper of slow-moving tides. As the Proterozoic world continues to cool, the atmosphere begins a transformation that will take hundreds of millions of years. The air once thick with methane and carbon dioxide starts to shift toward a new chemical balance shaped not by geology alone, but by life itself. The first signs are subtle, a faint brightening of the sky, a trace of blue appearing where once there was only copper haze. Sunlight filters more easily through thinning gases scattering across the oceans that now reflect a softer, clearer light. Yet this calm surface conceals immense chemical tension. The gases that once trapped heat begin to interact with the oxygen, slowly leaking from microbial photosynthesis. Reactions occur invisibly at the boundaries between sea and sky, transforming both. The oxygen that escapes from shallow waters meets methane in the air, producing carbon dioxide and water vapor. This exchange weakens the greenhouse effect and global temperatures begin to fall. The change does not happen evenly. Some regions remain warm under volcanic emissions, while others cool under thickening clouds of ice crystals high in the stratosphere. The planet's climate begins to oscillate, testing the limits of stability. As oxygen levels rise in some regions, methane, a potent greenhouse gas, is destroyed faster than it can be replaced. Cooling accelerates and parts of the globe may experience the first hints of glaciation. Ice creeps down from polar regions, carving faint scars into the continents. For the first time, sunlight reflects from white surfaces, rather than being absorbed by dark rock or ocean, amplifying the chill. Yet even as the world cools, life adapts. Microbial colonies persist beneath thin sheets of ice, finding refuge where liquid water remains. Beneath the oceans, chemical gradients sharpen. In shallow waters, oxygen from photosynthetic organisms begins to accumulate, but in the deeper layers, the old anoxic conditions still dominate. Hydrogen sulfide methane and ferrous iron continue to circulate, forming distinct chemical zones. The upper layers shimmer with oxygen and light, while the depths remain dark and reducing. Microbes evolve to exploit these boundaries, living precisely where the two worlds meet. Some species learn to tolerate oxygen, building internal mechanisms to detoxify it. Others retreat into the sediments where they can continue their ancient chemistry undisturbed. This coexistence marks a delicate equilibrium, one that will persist through much of the Proterozoic. Volcanic activity remains frequent along spreading ridges and subduction zones. Each eruption releases clouds of gas carbon dioxide, sulfur, dioxide, methane that mix into the atmosphere and temporarily reverse cooling trends. The air thus fluctuates between warmth and chill, never quite reaching full equilibrium. In these shifting conditions, weather systems strengthen. Winds begin to distribute moisture more evenly across the planet, bringing rainfall to regions that were once deserts of bare rock. The hydrological cycle, powered by sunlight and gravity, becomes a key force in shaping the planet. Rivers carve channels through the early crust, carrying sediments into deltas and basins, where they settle into new geological layers. The oxygen rising from the oceans begins to react with gases released by volcanoes. Sulfur compounds oxidize into sulfates, which fall back to Earth as acid rain, weathering rocks more quickly and feeding ions back into the sea. This feedback loop accelerates chemical evolution. The land, though still lifeless, becomes an active participant in the planet's metabolism. Over eons, the surface minerals alter, creating oxides and clays that lock away carbon. The slow drawdown of carbon dioxide helps maintain cooler global temperatures and further stabilizes the climate. In time, this regulation will make the atmosphere suitable for more complex life. Above these processes, the sky brightens further. With less methane to block ultraviolet light, a new danger emerges. Radiation from the sun reaches the surface in greater intensity. but the oxygen accumulating in the air begins to form ozone high in the atmosphere. This thin shield, composed of molecules of 3 oxygen atoms, absorbs ultraviolet radiation, preventing it from sterilizing the surface. The ozone layer's appearance is another turning point, a form of protection born directly from life's waste product. The same oxygen that threatened early microbes by corroding their enzymes now shapes a safer environment for future evolution. As time passes, the visual character of the planet changes. The copper haze fades entirely. Skies deepen into blue, and clouds appear whiter and more defined. The sun, seen from the surface, shines through an atmosphere now thinner and more transparent than in earlier ages. The oceans mirror that clarity, glowing with shades of green and turquoise in the shallows, where photosynthetic life thrives. Yet the air is still far from breathable by modern standards. Oxygen remains a small fraction of the total composition, just enough to change chemistry, but not enough to support animals. The rest is still nitrogen and carbon dioxide, remnants of the planet's primordial breath. Within the atmosphere, new cycles begin to link. Carbon moves from air to water to rock in a continuous exchange. When volcanoes erupt, carbon dioxide returns to the air. When rain falls on silicate rocks, carbon is pulled from the atmosphere into the sea. There it reacts with calcium to form carbonates that settle to the ocean floor. Each of these cycles operates over millions of years, yet together they create balance, a geochemical thermostat that keeps the planet neither too hot nor too cold. This self-regulating behavior, born from the interaction of air, water, and stone, marks the first faint glimmer of planetary homeostasis. Meanwhile, the sun grows slightly brighter as it ages, emitting more energy than it did in the Archean. The increase is gradual, but its effect is magnified by the thinning greenhouse gases. The competing forces of a brightening sun and a cooling atmosphere nearly offset one another, keeping Earth's average temperature within a narrow range that allows water to stay liquid. This coincidence, delicate and improbable, defines the character of the Proterozoic world, a planet balanced between ice and fire, stability and change. Storms sweep across the continents, their rains etching channels into volcanic plateaus. Lightning flickers through thick clouds, discharging energy into the growing oxygen content of the air. Each flash produces small amounts of nitrate, another molecule vital for life. Carried by rain into the oceans, these compounds feed microbial growth, closing yet another loop in the planet's evolving chemistry. In this way, the weather becomes part of life's support system. Every wind, every storm contributes to the slow enrichment of the biosphere. As the centuries of deep time continue, the new atmosphere begins to interact more strongly with the crust. Oxidation spreads through surface rocks, turning their minerals red and brown. Iron, once bound in black silicates, now rusts into hematite and limonite, creating vivid landscapes along the edges of ancient continents. When erosion carries this material into the sea, it settles as alternating layers of iron and silica. These banded iron formations stretching across the ocean floor are silent testimony to the balance between oxygen production and consumption. Whenever oxygen increases, iron oxidizes and sinks. When it declines, the oceans darken again. Through this cycle, the atmosphere's rise and fall are recorded in stone. The sky above this ancient world is no longer a veil of gas, but an active engine of transformation. Winds redistribute heat between equator and poles. Clouds form and dissipate, reflecting sunlight and regulating temperature. The interaction of air and water becomes rhythmic, producing seasonal patterns, though continents drift and climates remain uncertain. The Proterozoic Earth, once chaotic, now breathes in slow pulses, its atmosphere alive with feedback and adaptation. By the end of this long interval, the planet looks outwardly serene. Oceans glisten beneath an open blue sky, continents shimmer with oxidized rock, and life continues its quiet labor beneath the waves. Yet within this calm lies the foundation of all that will follow. The shift from methane to oxygen has reshaped the chemistry of the planet, altering its color, temperature, and destiny. The air that once choked life now begins to sustain it. The world has taken its first true breath, and the echo of that breath will guide the ages to come. In the quiet heart of the Proterozoic world, the oceans are both mirror and engine of change. They cover most of the planet's surface, their vastness dwarfing the emerging continents. Beneath their calm exterior lies a chemistry in flux, a slow and patient exchange between atmosphere and seafloor that determines the course of Earth's future. Each wave that laps against the barren coasts carries with it gases drawn from the air, oxygen, carbon dioxide, and nitrogen, all dissolving into the surface layers of the sea. The movement of these gases into and out of the water becomes one of the great regulating systems of the planet. Oxygen from the atmosphere mixes downward, while carbon dioxide rises in bubbles from volcanic vents below. Between them, in this meeting place of gas and liquid, an invisible balance forms that shapes both climate and life. The surface waters are shallow and sunlit, stirred constantly by wind and tide. Here photosynthetic microbes thrive, turning sunlight into energy and releasing oxygen into their surroundings. Yet the ocean is not uniform. Beneath the illuminated layer lies a deep and dark expanse where oxygen cannot penetrate. In those depths, ancient forms of life continue to rely on chemical energy, consuming iron, sulfur, and methane as they have for billions of years. The two worlds, one ruled by light and oxygen, the other by darkness and chemistry, exist side by side, separated by only a few hundred meters of water, but divided by entirely different ways of life. The boundary between them is fragile, constantly shifting with current, storms, and seasons. The oxygen produced in the surface waters reacts quickly with the iron dissolved below, forming rust-colored particles that sink to the bottom. Each flake of oxidized iron is a fragment of planetary transformation, the physical record of oxygen entering the sea. Over time, these particles accumulate into thick layers on the ocean floor, alternating with bands of silica and clay. The pattern continues for millions of years as life breathes in sunlight and exhales minerals. These sediments will one day harden into rock, preserving the evidence of this slow conversation between biology and geology. In the Proterozoic, however, they are still loose and shifting, stirred by deep currents and reshaped by the restless crust below. Chemical reactions ripple through the water column. Carbon dioxide absorbed from the atmosphere combines with calcium and magnesium released from eroding continents, forming carbonates that drift down as microscopic grains. These grains accumulate alongside the iron oxides, trapping carbon within the seafloor and gradually drawing it out of the air. This process stabilizes the planet's temperature over immense timescales, preventing runaway warming despite the sun's increasing brightness. Each cycle of absorption and burial acts as a breath, the ocean inhaling and exhaling gases in rhythm with the geological heart of the Earth. Yet the balance remains delicate. Volcanic eruptions pour carbon dioxide and sulfur compounds back into the air, some of which return to the sea in rainfall. The acidity of this rain dissolves minerals on the continents, washing ions into the water and altering its chemistry once more. In some regions, particularly near volcanic arcs and mid-ocean ridges, hydrothermal vents release superheated fluids rich in metals. These fluids rise through cold seawater, precipitating minerals that form chimneys of black and white smoke. Around them, microbial communities cluster, feeding not on sunlight, but on the chemical energy of hydrogen sulfide. These microbes form the base of ecosystems that endure in total darkness, demonstrating that life can thrive wherever energy flows, whether from the sun or from the interior of the Earth. Currents circulate slowly across the globe. Driven by temperature and salinity differences, they transport nutrients and oxygen from one region to another, connecting distant oceans into a single planetary system. Where cold water sinks at the poles, it carries dissolved gases into the depths. Where warm water rises near the equator, it releases them again. This circulation redistributes heat, moderates climate, and sustains the chemical gradients that life depends upon. It is a process so gradual that a single circuit may take thousands of years, yet over geological time it sculpts the rhythm of the entire biosphere. The ocean floor itself is not fixed. Along spreading ridges, molten rock pushes upward, creating new crust that cools and cracks as it moves away. At subduction zones, old crust plunges back into the mantle, carrying with it sediments and trapped water. This recycling releases gases that return to the atmosphere through volcanoes, closing the loop between sea air and stone. The interaction of tectonic motion and ocean chemistry ensures that no part of the planet remains static. Even the calmest seafloor is part of a dynamic system that breathes and circulates on planetary scales. As the oceans evolve, they begin to influence the behavior of the atmosphere more profoundly. The uptake of carbon dioxide reduces greenhouse warming, allowing temperatures to fall further. Ice sheets expand on high plateaus and near the poles, reflecting sunlight and amplifying cooling. Yet the oceans also act as a buffer, storing heat and releasing it slowly, preventing the planet from freezing entirely. The balance between these opposing forces depends on the composition of the water, the activity of life within it, and the shifting shapes of the continents that direct its flow. The result is a planet in equilibrium, neither frozen nor scorched, capable of sustaining slow, continuous evolution. In shallower seas, microbial mats blanket the seafloor. These communities trap sediment and create layered structures of carbonate and organic material. When tides recede, the mats dry and crack, only to be rebuilt when water returns. Over time, they thicken into stromatolites, domes, and columns that rise from the seabed like stone gardens. Each layer represents a day's work of microbial growth, a record of sunlight captured and oxygen released. The abundance of stromatolites during the Proterozoic suggests that photosynthetic life had spread across nearly every suitable coastal environment. Their presence not only increased oxygen production, but also provided microhabitats for other organisms, promoting greater ecological diversity. The chemical composition of the ocean continues to shift as these processes accumulate. Iron becomes scarce as it binds with oxygen, while sulfate levels rise as sulfur from volcanic gases oxidizes. These changes favor new metabolic strategies among microbes. Some evolve to use sulfate instead of oxygen, producing hydrogen sulfide as a byproduct. Others begin to store energy in organic molecules that can be broken down, later a primitive form of respiration. Each adaptation allows life to exploit the subtle gradients of chemistry that ripple through the ocean. The result is a biosphere of immense complexity at microscopic scales, invisible yet profoundly influential. As the eons pass, the ocean's slow breath deepens. Oxygen continues to rise, though never uniformly. Periods of relative stability alternate with sudden deoxygenation events, possibly triggered by tectonic upheavals or changes in circulation. During these intervals, vast areas of the ocean become anoxic, again suffocating many microbial communities. When oxygen returns, new species appear to replace those lost. This recurring rhythm of expansion and contraction becomes one of the defining patterns of Proterozoic life. From orbit, the planet would now appear more familiar. Blue oceans dominate, streaked with white clouds and edged by the dark outlines of continents. The atmosphere, though still thin by modern standards, reflects sunlight in hues of sapphire and silver. The world below is quieter than ever before, governed by cycles too slow for any observer to notice. Yet in the silence, profound change continues. The oceans breathing in gases from the sky and exhaling them again through vents and volcanoes act as the lungs of the early Earth. Each pulse carries the planet closer to equilibrium, preparing the stage for the next transformations to come: the rise of oxygen in earnest, and the reshaping of a world that is learning molecule by molecule how to sustain life. The slow respiration of the Proterozoic world gathers strength until it reaches a turning point known as the Great Oxidation Event, a transformation that forever changes the chemistry of the air, the colour of the oceans, and the destiny of life. For billions of years, oxygen produced by photosynthetic microbes had been absorbed by minerals reacting with iron, sulfur, and methane in the atmosphere and sea. But the Earth's capacity to consume oxygen is finite. When those sinks begin to fill, oxygen starts to accumulate in the air faster than it can be removed. The change unfolds not in sudden violence, but in a long, steady ascent, as if the planet takes its first deep breath after an eternity of holding it in. Gradually, the balance of gases shifts. Methane, once abundant, is destroyed by the growing presence of oxygen breaking into carbon dioxide and water vapor. This chemical reaction alters the planet's climate profoundly. Methane had been a powerful greenhouse gas trapping heat close to the surface, but carbon dioxide is weaker. As methane vanishes, temperatures drop. The air clears, becoming more transparent, and sunlight begins to reflect more strongly from clouds and ice. Earth cools under its own breath. In the oceans, the rise of oxygen triggers another cascade of changes. Iron, once dissolved freely in seawater, now reacts with oxygen to form rust-coloured precipitates that sink to the sea floor. The once green or grey depths turn reddish as iron oxides spread like dust across the basins. Over millions of years, these deposits accumulate into vast layers of banded iron formations, alternating stripes of iron and silica that record the pulses of oxygenation. Each layer marks a phase in which life's influence reached further into the environment. The red bands are the signature of a planet learning to live with air. The microbial world is both the cause and the victim of this transformation. Many ancient species cannot tolerate oxygen, which is a reactive and corrosive molecule that damages their enzymes and membranes. As oxygen concentrations rise, these anaerobic organisms retreat into sediments, deep waters, or hydrothermal vents where the old reducing chemistry still reigns. Some go extinct, unable to adapt. Others find refuge in the oxygen-free pockets that remain along continental shelves or within the crust. In their place, new lineages evolve that not only endure oxygen, but exploit it, using it to break down organic matter more efficiently. This innovation, cellular respiration, yields far more energy than fermentation, or chemical metabolism, laying the foundation for the evolution of larger and more complex life forms. The atmosphere itself undergoes a slow but inexorable transformation. Over tens of millions of years, oxygen levels climb from almost nothing to a few % of the air. It is still far below the concentration humans breathe today, but enough to oxidize minerals across the continents. Rocks at the surface begin to weather differently, turning red and brown as iron within them reacts with air. The world takes on a new palette of color-rusted mountains, ochre plains, and pale blue skies. The chemical fingerprints of this shift are preserved in ancient soils and sediments that still bear traces of early oxidation. The cooling caused by methane loss may have driven one of the first global glaciations. Ice advances across the continents, reaching near the equator in some regions. The frozen surface reflects sunlight, deepening the chill. Yet volcanoes continue to release carbon dioxide, which accumulates in the air as weathering slows beneath the ice. Eventually, the greenhouse effect strengthens again, melting the frozen world and restoring liquid oceans. This cycle of freeze and thaw may have repeated several times during the Proterozoic, each episode linked to the oscillating balance of gases in the atmosphere. In this way, life and climate become inseparable, each influencing the other through chemistry that spans the globe. Deep beneath the ocean surface, the consequences of oxidation are equally dramatic. Sulfide minerals on the seafloor begin to dissolve as oxygen penetrates deeper into the water column. The chemistry of nutrients changes, altering the availability of phosphorus, nitrogen, and trace metals that life requires. These shifts ripple upward through the food web, controlling where and how microbial mats can grow. The ocean becomes layered, an upper oxygenated zone teeming with photosynthetic life, and a lower anoxic realm still inhabited by archaic forms. The boundary between them moves with currents, storms, and tectonic change, creating a dynamic world in which adaptation is constant. The Great Oxidation Event is not a single moment, but a drawn-out transition lasting hundreds of millions of years. Geological records show alternating periods of high and low oxygen, suggesting that the planet struggled to find equilibrium. Each rise in oxygen sparked feedback loops that cooled the climate and reduced life's productivity, causing oxygen to drop again. When volcanic activity increased, releasing new gases, oxygen fell further. When continents eroded, releasing nutrients to the sea, photosynthetic microbes flourished and oxygen rose once more. Through this rhythmic exchange, the Earth learned to balance its internal cycles. The eventual stabilization of oxygen levels marks the beginning of a new planetary regime, one where biological and geological processes are intertwined in feedback systems that maintain long-term stability. The magnetic field generated by convection in the outer core plays a quiet but essential role in this transformation. By deflecting solar wind, it prevents the new atmosphere from being stripped away into space. The faint auroras that shimmer near the poles become brighter, as oxygen and nitrogen interact with charged particles, painting the upper sky with green and red light. These displays, unseen by any eye, mark the birth of the modern air. Without this magnetic shield, oxygen would not have endured. With it, the planet retains the capacity to sustain complex chemistry indefinitely. Over time, the new atmosphere begins to shape the behavior of the crust. Fires become possible wherever lightning strikes dry land, consuming organic matter and returning carbon to the air. The carbon cycle expands its reach from sea to shore. Although vegetation has not yet appeared, microbial films may already coat damp surfaces, darkening the rocks and capturing trace nutrients from rainwater. These primitive biosignatures mark the first faint invasion of land, though life still belongs overwhelmingly to the sea. The Great Oxidation Event is often described as a planetary revolution, yet to the planet itself, it is more like a slow unfolding, a gradual reorganization of systems that had been operating for billions of years. The rise of oxygen changes everything quietly: the color of rocks, the composition of the air, the behavior of volcanoes, even the way light scatters through the sky. For the first time, the horizon glows with the soft blue that will define Earth for the rest of its history. By the end of this immense transition, the planet stands transformed. The air carries enough oxygen to oxidize minerals on every exposed surface. The oceans, once green with dissolved iron, now shimmer in deeper shades of blue. Life adapts to new niches, some species vanishing, others evolving pathways that use oxygen as fuel. The stage is set for the next advance, the emergence of stable continental masses, rising mountains, and the quiet spread of microbial architecture that will mark the middle Proterozoic world. The Earth breathes steadily now, its atmosphere alive and self-sustaining, its cycles locked into the slow rhythm that will guide all ages to come. As the Great Oxidation Event deepens the visible record of Earth's transformation, spreads across the ocean basins in the form of rust. What begins as a chemical reaction at microscopic scales soon reshapes the surface of the planet. The iron dissolved in ancient seas, once invisible and abundant, now encounters the rising tide of oxygen released by photosynthetic life. Each meeting of these elements produces tiny particles of iron oxide that drift downward like mineral snow. They settle on the seafloor in slow, endless accumulation, forming deposits of red and grey that blanket vast regions of ocean crust. Layer upon layer builds through time, alternating as the oxygen levels in the water fluctuate with the seasons, the tides, and the rhythms of microbial growth. These banded iron formations become some of the most enduring geological records in Earth's history, silent layers that trace the breath of a young atmosphere learning to balance itself. The chemistry behind this transformation is simple, yet profound. In the absence of oxygen, iron exists in a soluble form easily carried through seawater. But once it reacts with oxygen, it transforms into rust, an insoluble mineral that sinks immediately. In this way, the presence of oxygen cleanses the ocean of iron, removing a metal that once dominated its chemistry. The process continues until nearly all dissolved iron is gone, leaving the water clearer and changing its hue from green to blue. The deep seas, once cloudy with metallic ions, become transparent and reflective, setting the stage for new interactions between sunlight and the living world below. With iron no longer abundant, other elements begin to take on greater roles in supporting life: phosphorus, nitrogen, and sulfur, each cycling through the oceans under new chemical rules defined by oxygen's presence. These vast deposits of rust do more than mark a change in colour. They alter the planet's thermal and tectonic balance. Iron oxides are dense and heavy, adding weight to the oceanic crust and influencing how it sinks and subducts beneath the continents. Over millions of years, the recycling of this oxidized crust returns material to the mantle, where it melts and re-emerges through volcanoes, releasing new gases into the atmosphere. This slow exchange connects the deep Earth to the surface, closing the loop between rock air and life. Through these cycles, the chemistry of the whole planet begins to act as one interconnected system. On the continents, oxidation leaves its mark as well. Rocks once dark with metallic minerals turn red as iron within them reacts with the oxygen-rich air. This reddening spreads across floodplains, deserts, and coastal zones, tinting entire landscapes with shades of ochre and sienna. Later generations will find these ancient soils paleosols and recognize them as evidence of Earth's first breathable air. Rainwater, slightly acidic from carbon dioxide, seeps into the ground and accelerates the transformation, dissolving iron and reprecipitating it as rust near the surface. The process thickens crustal layers with iron-rich horizons that record the passage from an anoxic to an oxygenated world. Even in the absence of plants or animals, the continents are alive with chemical weathering, their surfaces changing hue and texture as if painted by the invisible hand of the atmosphere. In the shallow seas where sunlight penetrates microbial mats, continue their quiet work. Each colony of cyanobacteria releases tiny bubbles of oxygen that gather beneath their gelatinous surfaces before bursting upward into the air. These bubbles glisten briefly as they rise, carrying the invisible agent of transformation. The oxygen not only oxidizes the iron in the water, but also reacts with dissolved sulfides, converting them into sulfates that mix with calcium to form gypsum and anhydrite. These minerals accumulate in coastal basins, further altering the balance of the ocean's chemistry. The once reducing world now becomes a place of oxidation, where every element finds new partners and new forms. The environmental consequences ripple outward. With less iron available in solution, some microbial species that depended on it for metabolism begin to decline. Others adapt by developing enzymes that use copper, molybdenum, or manganese instead. This shift in biochemistry opens new evolutionary pathways and gradually increases the metabolic diversity of life. The biosphere becomes more complex, not through visible structures, but through invisible innovation, new molecular strategies that will later support multicellular organisms. Oxygen, initially a toxin to many microbes, becomes the foundation for biological energy systems far more efficient than any that came before. As the oceans clear, sunlight penetrates deeper, stimulating photosynthesis in layers once too dim for it. Productivity increases near continental shelves where nutrients are plentiful, and oxygen production accelerates. The feedback between light, life, and chemistry tightens. More light produces more oxygen, which removes more iron, which clears the water further, allowing still more light to enter. In this positive loop, the world transforms itself through the quiet persistence of microbial activity. Yet these processes remain fragile, easily disrupted by shifts in temperature, tectonic movement, or volcanic gas release. Periods of anoxia still return from time to time, leaving darker bands in the geological record that testify to the instability of this early balance. The iron formations themselves grow to continental scale, some stretching for thousands of kilometers and reaching thicknesses of hundreds of meters. When these layers eventually rise through tectonic uplift and erosion, they will form the cores of mountain ranges and the sources of future mineral wealth. But in the Proterozoic, they lie hidden beneath the sea, accumulating grain by grain. The red particles, once suspended in water, now settle into silence, compressing under their own weight into rock. Each grain is a fossil of chemistry, each layer a breath of time. The world is writing its autobiography in rust. At the same time, the decline of methane caused by oxygen's rise cools the planet, allowing glaciers to advance in high latitudes. Ice scrapes across the red-stained rocks, grinding them into fine dust that drifts into the sea. The iron within this dust reacts again with oxygen as it settles, perpetuating the cycle of oxidation even during glacial periods. Thus, the processes of air, water, and ice intertwine in a feedback that reshapes not only the surface, but the climate of the Earth. The Great Oxidation Event, now well underway, is not merely a change in chemistry, it is a reorganization of planetary energy. Beneath the continents, the mantle responds to the cooling surface. Convection slows slightly, allowing the crust to stabilize. This stability permits the formation of larger continental masses that resist subduction. These continents will serve as platforms for weathering erosion and the continued cycling of iron and carbon between the crust and the oceans. The interaction of oxygen with minerals in the crust also releases trace elements such as phosphorus and silica that nourish marine life, further linking geology with biology. By the end of this long episode, the world has altered its face entirely. The skies are bluer, the oceans clearer, and the rocks stained with the memory of oxygen's rise. The red beds and banded iron formations remain as enduring witnesses, stretching through the crust like pages in a book. The balance between oxygen production and consumption still fluctuates, but the trend is irreversible. The planet has crossed a threshold from which there is no return. Rust has become the color of progress, the physical emblem of Earth's new state. What began as a chemical reaction now defines the entire identity of the world, a place where rock, water, and air are bound together by life's invisible breath, and where every grain of iron oxide carries within it the quiet signature of transformation. As oxygen reshapes the surface of the planet, the architects of this transformation remain small, unseen, and silent. The microbial world of the Proterozoic dominates every coastline lagoon and shallow basin, forming living carpets that bind sediment and light together. These colonies, made primarily of cyanobacteria, are the quiet engines of planetary change. They cover tidal flats and continental shelves in vast mats, their filaments weaving through layers of sand and silt. Each cell absorbs sunlight through pigments adapted to the faint filtered rays that pass through the thick atmosphere. Through photosynthesis, they split water molecules, releasing oxygen as waste and forming organic carbon that fuels the slow metabolism of the planet. The rhythm of day and night governs their activity. When sunlight falls on the shallow sea, the mats pulse with microscopic life. When darkness returns, they rest, leaving only the slow bubbling of gases from their upper layers. These microbial communities are both ancient and resilient, capable of surviving desiccation, flooding, and burial. Over millions of years, their activity creates stromatolites-layered rock structures that rise from the seabed like frozen reefs. Each layer represents a growth season, a thin film of microbial life that trapped sediment, secreted mucus, and then fossilized as the next generation grew above it. Stromatolites form domes, columns, and rippling mounds that spread for kilometers along ancient coasts. They are among the oldest living ecosystems on Earth, and among the few biological structures visible to the naked eye in the Proterozoic world. The landscapes they create are alien yet familiar shallow lagoons shimmering with blue-green mats, tidal flats patterned with hexagonal cracks, and quiet shorelines lined with mounded reefs of stone built entirely by bacteria. The chemical environment of these habitats is complex. Oxygen concentrations vary by the hour, rising in sunlight and collapsing at night. Beneath the surface of each mat, layers of microbial communities specialize in different forms of metabolism. The uppermost layer contains photosynthetic cyanobacteria that release oxygen. Just beneath them live bacteria that use sulfur compounds or methane. Deeper still are organisms that thrive in total darkness, breaking down organic matter left behind. This vertical structure allows the mat to recycle nutrients efficiently, forming a miniature version of the planet's own cycles. It is within these microscopic worlds that the foundations of all later ecosystems are established. The interactions between oxygen-producing and oxygen-consuming microbes generate balance, stability, and chemical variety that will one day support multicellular life. Despite their power, these organisms are fragile. The slightest change in temperature, salinity, or sunlight can collapse entire mats. Storms tear them from the seafloor and shifting tides bury them beneath sediment, yet they always return regrowing from the fragments that survive in the shallows. Their persistence over billions of years speaks to the adaptability of life at its simplest form. While continents drift and climates change, the microbes continue their slow work, altering the planet molecule by molecule. In the clear shallows, the expansion of microbial mats accelerates the production of oxygen and the burial of organic carbon. As more carbon becomes trapped within sediments, less remains in the atmosphere as carbon dioxide. This subtle shift reduces greenhouse warming, leading to further cooling of the global climate. The microbes indifferent to these distant consequences continue their silent labour, unaware that their photosynthesis is reshaping not only the air they breathe, but the temperature of the world itself. In this way, biology begins to act as a planetary thermostat, regulating heat through chemistry, long before complex life appears. The light that sustains these microbes filters through an atmosphere still dense with dust and volcanic gases. The sun appears larger and redder in the sky than it will in later ages, its rays scattered by particles high in the air. In this dim glow, photosynthesis remains efficient, but it favours pigments that absorb red and infrared wavelengths. The result is a world tinted in shades of blue, green and brown, where colour itself becomes a reflection of chemical function. The pigments within cyanobacteria absorb light not for beauty, but for survival, and their success covers the Earth's coasts with living colour that no eye yet sees. Deeper within the ocean, away from sunlight, other microbes adapt to the presence of oxygen diffusing slowly downward. Some evolve enzymes that protect them from oxidation, allowing them to survive at the boundary between oxygenated and anoxic waters. Others exploit the new chemistry to oxidize metals or sulfur compounds, using oxygen as an energy source rather than fearing it. This transition represents one of the most profound biological innovations in history, the ability to harness oxygen for metabolism. It provides a far more efficient means of releasing energy from food, setting the stage for the evolution of eukaryotic cells that will one day dominate the biosphere. On the seafloor, the remains of dead microbes accumulate in fine layers, adding organic material to sediments. Over time, these deposits compact and transform into shale storing carbon deep within the crust. The burial of this carbon prevents its return to the atmosphere, allowing oxygen levels to rise further. This interplay between life and geology creates a feedback loop that sustains the oxygenation process. Life modifies its environment, and the environment in turn shapes the path of evolution. The planet has become a self-regulating system, though the organisms responsible remain oblivious to their influence. The structure of microbial mats changes as conditions evolve. In some regions, iron becomes scarce, forcing microbes to adapt to new nutrient limitations. In others, sulfate concentrations increase, allowing the rise of sulfur-cycling bacteria that coexist with the cyanobacteria above them. The mats grow more stratified and complex, their chemical gradients steepening as they diversify. This vertical layering is an early form of ecological zoning, with each layer performing a specific role in the recycling of matter. The boundaries between these layers shift with the tides, creating dynamic systems that mirror the slow but steady rhythms of the larger planet. Occasionally, volcanic eruptions darken the skies for years, reducing sunlight and forcing the photosynthetic communities into dormancy. When the air clears, they return, often more extensive than before. This resilience hints at a remarkable stability built into the biosphere even when temporarily silenced. Life resumes its cycles with persistence. The Proterozoic world, though fragile in appearance, operates with quiet endurance. Over millions of years, the expansion of microbial ecosystems alters coastlines. Sediment trapped by stromatolites builds new shoals and platforms that change the shape of the seas. Some lagoons fill entirely, leaving fossilized reefs exposed to erosion. Rainwater dissolves and reprecipitates the minerals within them, preserving the textures of microbial growth in exquisite detail. These structures, once alive, become monuments to persistence. They will survive into the modern era, providing scientists with a window into Earth's earliest life. As continents continue to drift, the distribution of shallow seas changes, and with them the extent of stromatolite ecosystems. Some vanish as seas deepen, or currents shift while others appear on new continental margins. Despite these fluctuations, the overall presence of microbial life remains universal. Nearly every coast bears its mats and reefs, its quiet colonies exhaling oxygen into the atmosphere. By the close of this long period, the surface of the Earth has settled into a steady rhythm. Oxygen rises and falls with the cycles of life, but no longer disappears entirely. The air is still thin, the land barren, the oceans simple, yet the foundation of complexity is in place. The microbes that built this world leave no voices, no movement visible to the eye, yet they alter every element of the planet, its air, its stone, its colour, and its temperature. They are the unseen engineers of stability, the architects of habitability. From their endless repetition of chemical reactions, the conditions for all future life emerge. Beneath the stillness of ancient seas, the smallest cells continue their slow construction of a breathable world, unaware that their quiet persistence has set in motion the long chain of events that will one day lead to forests, animals, and consciousness itself. Beneath the calm oceans of the Proterozoic, the deep interior of the planet remains restless. Heat rising from the mantle drives the slow dance of continents, moving them across the surface in cycles that span hundreds of millions of years. This motion is invisible from day to day, but over geological time it reshapes the face of the Earth. Fragments of crust drift together, collide, and separate again, forming and breaking supercontinents in an endless rearrangement of land and sea. The first of these great unions, known as Nuna, begins to take shape around the middle of the Proterozoic. Its assembly is a slow process marked by the grinding of tectonic plates, the birth of mountain ranges, and the creation of deep ocean basins. Beneath the continents, magma wells up at spreading ridges and cools into new crust, while elsewhere older crust plunges back into the mantle through subduction. These movements recycle material between surface and interior, driving both geological and atmospheric change. The continents themselves are far smaller than those of the modern world, yet they are already stabilizing. Their cores, called cratons, are built of ancient rock that resists melting and deformation. Around these cores, younger volcanic arcs and sediments accrete, thickening the land masses and expanding their edges. When two continents collide, the crust buckles and folds, thrusting mountain belts high above the sea. These new ranges, though quickly worn down by erosion, become powerful agents of chemical transformation. Rainwater weathers the uplifted rock, releasing minerals and nutrients that flow into rivers, and finally the ocean. There they feed microbial life, linking tectonic activity to biological productivity. Through these cycles, geology and biology intertwine ever more tightly, each influencing the other in slow but measurable ways. Nuna's assembly brings together fragments from across the globe, creating a vast landmass surrounded by broad, shallow seas. The interior of the supercontinent is dry and barren, scorched by sunlight and stripped of vegetation. Winds sweep across the plains, carrying dust that settles along the coasts, where it mingles with sediments and becomes part of the growing record of continental drift. Along the margins of Nuna, volcanic activity is intense. Magma erupts in great sheets of basalt, adding new crust and releasing gases that enrich the atmosphere with carbon dioxide and sulfur compounds. The balance of gases shifts again, altering climate and ocean chemistry. Yet even as these eruptions darken the skies, photosynthetic life continues drawing carbon from the air and releasing oxygen in steady rhythm. Over time, Nuna begins to fragment. Heat trapped beneath the thick crust weakens it from below, opening rifts that flood with basaltic lava. As these rifts widen, seawater pours in, creating new oceans and separating the landmasses once more. The movement is slow, measured in centimeters per year, yet its effects are planetary. The rearrangement of continents changes the flow of ocean currents, redistributing heat and nutrients. Climate zones shift as the shape of the oceans evolves, and rainfall patterns adjust accordingly. These changes influence the distribution of microbial communities, which adapt to new coastlines and fresh basins of shallow water. Life follows the motion of the crust, colonizing every available niche, left in the wake of tectonic change. The cycle of supercontinent formation and breakup repeats again and again through the Proterozoic. After Nuna comes Rodinia, another vast union of continents that will later drift apart to form yet more configurations. Each cycle affects the balance of gases in the atmosphere and the chemistry of the oceans. When continents converge, mountain building increases weathering, drawing carbon dioxide from the air and cooling the planet. When they separate, volcanic activity intensifies, releasing carbon dioxide and warming the world once more. The Earth's climate oscillates gently within this tectonic rhythm, maintaining conditions that remain suitable for life. This feedback between the crust and the atmosphere acts as a geological heartbeat, steady and self-correcting. The moving continents also influence the magnetic field. As the planet's iron core continues to churn, its rotation interacts with the mantle above, producing shifting magnetic poles. The rocks formed along spreading ridges record these reversals, preserving the direction of the field at the moment they cooled. Over time, these magnetic signatures trace the wanderings of the continents across the globe. To a modern observer, they would appear as the lines of a grand, slow dance choreographed by heat and gravity. On the surface, the formation of mountain belts changes the landscape dramatically. High peaks rise, catching moisture from the atmosphere and feeding rivers that erode them grain by grain. Sediment carried by these rivers builds deltas and floodplains that support dense microbial mats. As the rivers reach the sea, they spread nutrients that stimulate photosynthesis, drawing yet more oxygen into the air. Every tectonic collision thus becomes an event of biological consequence. Even the grinding of one continent against another leaves traces in the chemistry of the ocean, linking distant processes through the universal medium of water. The stability of the continental crust allows the development of extensive shallow seas, ideal environments for photosynthetic life. These platforms, flooded and exposed with the rise and fall of sea level, act as vast reactors where sunlight, minerals and microbes combine. Stromatolites grow thick and widespread along their edges, capturing sediments that build new layers of limestone and dolomite. Each cycle of transgression and regression leaves behind bands of carbonate rock that record the pulse of tides and climate. In this way, tectonic motion writes its story not only in mountains but in the quiet language of sediment. Within the mantle convection, currents shift constantly, dragging continents through changing latitudes. A region that once lay near the equator may over tens of millions of years drift toward the pole. These movements alter the distribution of sunlight and heat, shaping the global climate. Glacial deposits found in rocks of this age suggest that ice occasionally reached low latitudes, perhaps when land masses gathered near the poles. The alternation between greenhouse and icehouse conditions reflects the balance between tectonic carbon release and biological carbon capture. The Earth's surface becomes a dynamic mosaic of environments: arid interiors, humid coasts, frozen highlands, and warm equatorial seas, all governed by the slow motion of the continents. At the boundaries where plates collide, subduction zones draw seawater deep into the crust, carrying with it sediments rich in organic carbon. When these materials melt and re-emerge in volcanic eruptions, they release gases that maintain the atmosphere's composition. The cycle ensures that the planet remains chemically active and that the air continues to interact with the rocks below. This deep circulation connects the biosphere with the geosphere, forming a continuous loop of matter that spans from the surface to the mantle and back again. Through these endless movements, the continents carve their stories into the surface of the world. Mountain ranges rise and erode away. Basins fill with sediment and later become rock. Seas open and close in patient succession. To the microbial life that carpets the coasts, these events unfold slowly beyond comprehension, yet they determine the conditions of survival. Each rearrangement of the land redistributes nutrients, shifts currents, and reshapes the face of the ocean. The Proterozoic Earth is no longer a static world, but a living system of stone and water driven by inner heat and guided by invisible convection. By the close of this stage, the continents have drifted into a configuration that anticipates new geological ages. The crust has thickened, the air has stabilized, and the oceans circulate with a rhythm established by tectonic force. The planet's internal energy continues to sculpt the surface, ensuring that no part of the world remains untouched by motion. Beneath the still blue sky, the continents glide like slow ships across an ancient sea, carrying the memory of their collisions and separations within the layers of their rocks. The movement is so gradual that life scarcely notices, yet it is this unending drift that maintains the balance of carbon, oxygen, and climate. The solid ground of the Earth, though it appears eternal, is in truth a traveller, a shifting stage upon which the drama of life quietly unfolds. The movement of continents brings with it the slow but powerful rise of mountains, and with mountains come the endless processes of erosion that feed the oceans with the raw materials of new worlds. During the Proterozoic, tectonic collisions compress and thicken the crust, lifting enormous belts of rock toward the sky. Their summits are sharp and barren, devoid of soil or vegetation, exposed directly to wind, rain, and temperature extremes. At these high altitudes, the air is thin, the sunlight harsh, and the cycles of heating and cooling fracture stone into fragments. Day after day, the peaks crumble grain by grain, and every particle that breaks loose begins a long journey back toward the sea. In these slow processes, the land itself becomes a source of transformation, a constant supplier of minerals that sustain the chemistry of the planet's surface. Rain falls upon the slopes, gathering into streams that cut deep channels through the young mountain ranges. The rivers carve their way down to the plains, carrying sediments of quartz, feldspar, and clay. Each drop of water wears away rock and carries with it the trace elements of the crust: calcium, magnesium, potassium, phosphorus. When these minerals reach the oceans, they alter its composition, feeding the cycles of life that depend upon them. The connection between mountains and microbes grows stronger with every storm. The erosion of stone becomes the nourishment of the sea, and the balance of the biosphere depends upon the steady breakdown of the land. On a geological scale, erosion acts as a feedback mechanism, linking tectonics, climate, and life. The uplift of mountain belts exposes fresh rock to the atmosphere, where it reacts with carbon dioxide dissolved in rainwater. This chemical weathering converts carbon dioxide into carbonate ions that wash into the ocean and eventually form limestone. Over millions of years, the process draws carbon out of the air, cooling the planet. When mountains grow, the world cools. When they wear away, volcanic outgassing restores warmth. The climate breathes in rhythm with the creation and destruction of stone, maintaining temperatures within a range that allows liquid water to persist. The mountains thus serve as regulators of global stability, acting through chemistry rather than motion. At the base of these ranges, the sediments accumulate into alluvial fans and deltas, where water slows and deposits its load. The grains settle by size and density, forming layers that will one day become sandstone, shale, and conglomerate. Each layer captures a moment in the long dialogue between land and sea. In shallow coastal zones, microbial mats colonize the newly formed sediments, stabilizing them with their sticky secretions. These mats trap fine particles of clay and silt, forming rippled textures that record the passage of tides and currents. Over time, such surfaces harden into rock, preserving the imprints of ancient life and the fingerprints of flowing water. The interaction between erosion and microbial growth creates new ecological niches. Nutrients released from the land fertilize the oceans, stimulating photosynthesis and increasing the production of oxygen. As oxygen rises, it reacts with iron and sulfur in seawater, precipitating minerals that settle as chemical sediments. These deposits mixed with the detritus from eroded mountains build thick sequences of layered rock. The continents grow outward through these accumulations, their edges fringed by sediments that solidify into the foundations of future land. In this way, destruction and creation proceed together. The wearing down of mountains provides the building materials for new continental crust. In the atmosphere above, the presence of oxygen begins to interact with weather itself. Lightning generated by storms along the mountain fronts oxidizes nitrogen in the air to form nitrates that dissolve in rain. When these compounds reach the ocean, they act as nutrients for microorganisms. The nitrogen cycle, which today supports all complex life, is already in motion during this ancient era. Each thunderstorm thus becomes part of the planet's metabolism, linking skyland and sea in a continuous exchange of elements. The visual landscape of the Proterozoic changes with the rise of mountains. The flat horizons of earlier ages give way to jagged ranges that cast long shadows across the plains. Glaciers carve deep valleys where climate permits their movement, grinding rock into fine powder that is carried by meltwater to distant basins. The fine sediments form vast mudflats and continental shelves, which in turn support flourishing microbial ecosystems. Even in their destruction, the mountains feed life. The interplay of uplift and erosion creates a dynamic equilibrium. As quickly as the crust thickens, it is leveled again, ensuring that the continents neither grow indefinitely nor disappear beneath the sea. Within the mountains themselves, metamorphism transforms the buried sediments into new minerals. Heat and pressure rearrange the atomic structure of rocks, creating schists, gneisses, and quartzites. These metamorphic layers preserve evidence of the conditions deep within the crust, the immense temperatures and pressures that accompany the collision of continents. Over eons, these rocks will be uplifted and exposed, revealing the inner workings of the planet. Every pebble in the rivers that flow from these ranges carries within it the memory of ancient mountains now vanished. The atmosphere responds to the rhythm of erosion as well. As more carbon dioxide is consumed by weathering, global temperatures decline, occasionally pushing the planet toward glaciation. Ice spreads from polar regions, reflecting sunlight and intensifying the chill. Yet volcanoes continue to exhale gases from the interior, replenishing carbon dioxide and warming the world again. These alternating intervals of cold and warmth mark the long stability of the Proterozoic climate, a balance maintained by the feedback between rock and air. Through these cycles, the Earth learns to regulate itself, its geology and atmosphere, operating together as a single system. Over time, the erosion of mountains alters the salinity of the oceans. The influx of dissolved ions increases the concentration of salts, changing the density and circulation of seawater. Currents deepen, carrying oxygen and nutrients to greater depths. This enhanced mixing supports life further from the surface and begins to prepare the oceans for more complex ecosystems. The process is slow but cumulative, and by the end of the Proterozoic, the chemistry of the seas has evolved from the iron-dominated world of the early Earth to the more balanced, oxygenated ocean that will nurture animals in the next era. The mountains that once towered above Nuna and later Rodinia gradually erode into gentle highlands. Their remnants scatter across the continents as ancient shields, flat expanses of exposed crystalline rock that form the stable cores of modern continents. These cratons are among the oldest surviving parts of the Earth's surface, their surfaces marked by countless cycles of uplift and decay. In their mineral grains lies a record of atmospheric oxygen, ocean chemistry and biological activity stretching back billions of years. The history of life is written not only in fossils but in the structure of stone. By the close of this stage, the Earth has achieved a new equilibrium. The continents are large and stable, the oceans deep and well mixed, and the air maintains a steady level of oxygen. The interplay of mountain building and erosion continues to drive the slow circulation of carbon and minerals between the crust and the sea. The planet's surface is no longer dominated by sudden catastrophe, but by steady transformation. From the quiet decay of peaks to the gentle accumulation of sediments, every grain of sand participates in the grand cycle of renewal. The world breathes through its mountains, drawing in carbon, releasing minerals, and maintaining the fragile conditions in which life can persist. The silence of the Proterozoic is not emptiness, but balance, the soundless rhythm of a planet in perfect motion sculpted by gravity, water, and time. Even as the continents find stability and mountains settle into long cycles of erosion, the planet remains restless beneath the surface. Deep within the mantle, convection continues to drive volcanoes, rifts, and oceanic ridges that release gases into the air and minerals into the sea. These invisible exchanges alter the balance of oxygen, carbon, and sulfur on a planetary scale. The Proterozoic oceans, though clearer than before, still carry immense chemical complexity. Beneath their blue surface lie waters stratified into distinct layers, oxygen-rich shallows above and oxygen-poor depths below. At the boundary where these worlds meet, sulfur becomes the element of survival. In the absence of light, microbes harness the chemical energy of sulfur compounds to sustain themselves, oxidizing or reducing them according to local conditions. The result is a world where life thrives in gradients, each layer of the sea home to a different metabolism. These sulfur-driven ecosystems generate hydrogen sulfide, a gas that smells faintly of decay and is toxic to most modern life. In the Proterozoic, however, it is a cornerstone of survival, circulating through the oceans as part of the slow respiration of the planet. At intervals, the balance between oxygen and sulfur collapses. Volcanic eruptions pour carbon dioxide and methane into the air, thickening the atmosphere and warming the planet. The heat increases evaporation, driving stronger rainfall that delivers more nutrients into the oceans. Microbial productivity surges, releasing greater amounts of oxygen into the shallows. Yet the organic matter produced in these blooms sinks into deeper layers, where it is consumed by bacteria that strip oxygen from the water. When this process accelerates, entire regions of the ocean become anoxic, again filled with hydrogen sulfide that seeps upward toward the surface. The sea takes on strange hues, green, purple, and red, as different microbes exploit the changing chemistry. Such episodes, known as euxinic events, can last for millions of years before oxygenation returns. In these times, the oceans truly become seas of sulfur, alive yet hostile, their surface calm, hiding a world of chemical tension beneath. The alternation between oxygenated and sulfidic oceans has profound consequences for the biosphere. Each shift reorganizes the distribution of life, eliminating species adapted to one chemistry and favoring others that can endure extremes. This slow rhythm of expansion and contraction becomes a form of evolutionary pressure, shaping the resilience of organisms and refining the biochemical pathways that will later support complexity. The sulfur cycle, driven by the interaction of microbes and volcanoes, becomes one of the main regulators of the Proterozoic environment. Climate follows its own rhythm. The drawdown of carbon dioxide by weathering and biological activity cools the atmosphere while volcanic outgassing replenishes it. At times, the cooling dominates and ice begins to spread from the poles toward lower latitudes. Glaciers advance across continents, carving grooves into the ancient bedrock. Snow reflects sunlight back into space, amplifying the cold in a feedback that deepens global freezing. The world edges toward what scientists call a snowball state, a time when much of the planet may have been covered in ice from pole to equator. In such conditions, the oceans lie beneath a frozen crust, yet liquid water persists below, warmed by geothermal heat and the faint light that filters through cracks. In these hidden depths, microbial life endures, clinging to hydrothermal vents and pockets of open water. The atmosphere thins as carbon dioxide is drawn down by the expanding ice, but volcanoes continue to emit gases that accumulate slowly over millions of years. When the concentration becomes high enough, the greenhouse effect returns, melting the ice in a dramatic reversal that floods the world once again. These alternating states of warmth and cold leave lasting marks in stone. Dropstones, pebbles carried by icebergs, fall into marine sediments, far from land, embedding themselves in layers of mud that later harden into rock. Such deposits provide silent testimony to the planet's cycles of freezing and thawing. Each glaciation scrapes the continents bare, erasing old landscapes and releasing minerals that feed new generations of life once the ice retreats. The repeated cleansing of the surface by ice and erosion resets the chemistry of the oceans, providing fresh nutrients that sustain photosynthesis when warmth returns. The Earth, through its alternations of sulfur and ice, learns resilience, purging and renewing itself with every long breath. The interplay between climate and chemistry is delicate. When the oceans are covered by ice, photosynthetic activity nearly ceases and oxygen levels drop. Anaerobic organisms dominate once more, producing methane and hydrogen sulfide. As the ice melts, sunlight returns, sparking explosive blooms of cyanobacteria that flood the atmosphere with oxygen. These bursts may trigger short-lived oxidizing episodes that deposit new layers of iron and sulfur minerals in the sediment. The planet oscillates between two states, one dominated by oxygen and light, the other by sulfur and darkness. This duality defines much of the Proterozoic experience, a world perpetually poised between stability and collapse, where life persists through cycles of scarcity and abundance. In volcanic regions, the chemistry grows even more complex. Submarine eruptions release iron and sulfide ions into the water, forming shimmering plumes of minerals that spread through the ocean like smoke. Microbes gather around these vent systems, exploiting the gradients of temperature and chemistry to harvest energy. These vent communities, though microscopic, are ecosystems in miniature. They include sulfur-oxidizing bacteria methanogens that feed on hydrogen and archaea that tolerate extreme heat. Some of these lineages will later give rise to symbiotic partnerships that form the basis of eukaryotic cells. In the dark pressure of the deep sea, the raw materials of complexity are quietly assembling. Above the continents record each climatic swing in alternating bands of glacial and interglacial deposits. Red beds mark intervals of warmth and oxidation. Grey tillites mark cold and reduction. Rivers cut through layers of ancient ice-carved stone, leaving behind polished surfaces that reflect the faint blue of the new sky. With each melt, the continents release floods that wash minerals into the sea, restoring its chemical diversity and supporting renewed photosynthetic activity. Over hundreds of millions of years, these long cycles of ice and thaw shape the balance between life and environment, ensuring that neither oxygen nor sulfur ever fully dominates. The combined effect of tectonic motion chemical weathering and biological feedback transforms the Proterozoic Earth into a planet of intricate equilibrium. Its oceans breathe between states of oxygen and sulfur, its air swings between clarity and haze, and its surface alternates between frozen silence and liquid motion. Each fluctuation reinforces the resilience of the biosphere. Microbes evolve strategies for every condition. Some endure freezing, others tolerate poison, and many retreat into the deep crust when the surface becomes hostile. Through these adaptations, life ensures continuity, even in the face of planetary extremes. By the end of this age, the world bears the scars of its long struggle between fire and ice. Thick layers of glacial debris rest above deposits of sulfur-rich shale, and oxygen once again fills the atmosphere to modest but stable levels. The oceans, no longer entirely toxic, begin to host diverse microbial lineages capable of coexisting under varying conditions. The continents are old and weathered, the air clearer than ever before, and the planet, though scarred by cycles of crisis, has achieved a new steadiness. From this balance of opposites, the stage is prepared for yet another leap in complexity. The Earth, tempered by sulfur and sculpted by ice, emerges stronger, its chemistry richer, and its systems more interconnected than at any time before. In the quiet aftermath of these upheavals, the seeds of new forms are already stirring in the depths, waiting for the next dawn of oxygen to bring them into view. In the wake of long ages of ice rust and chemical flux, the oceans of the Proterozoic grow stable enough for a new kind of life to appear: cells that contain within them a nucleus. These eukaryotic cells are not sudden inventions, but the result of countless microscopic experiments played out over hundreds of millions of years. The simple prokaryotic world, built of cells without internal compartments, begins to give rise to organisms with enclosed DNA, specialized structures, and the capacity for greater complexity. The origins of this transition are hidden in symbiosis. Some ancient microbes engulf others but do not digest them. Instead, the two form a partnership. One provides energy, perhaps by using oxygen. The other offers protection and nutrients. Over time, the relationship becomes permanent. The internalized partners evolve into organelles, mitochondria, in some lineages chloroplasts in others. The once separate beings merge into a single organism, more efficient, more adaptable, and able to exploit the oxygen-rich world that the older microbes created. Within the oceans, these new eukaryotic cells begin to spread. They are larger than bacteria, often many times their size, and their membranes allow complex chemistry to occur in isolated compartments. The nucleus shields genetic material from the turbulence of the cytoplasm, ensuring more stable control of reproduction and repair. These innovations seem small but transform the logic of life. For the first time, cells can store, process, and express information with precision. They can maintain internal balance even as external conditions fluctuate. This stability allows them to evolve new shapes, behaviors, and life cycles, forming colonies, filaments, and floating spheres that drift through the water. The rise of eukaryotes is both a biological and a chemical event. The oxygen accumulated during previous ages creates an environment where energy can be harvested more efficiently. Through aerobic respiration, eukaryotic cells extract many times more energy from food than anaerobic bacteria can. This surplus energy fuels the synthesis of complex molecules, proteins, lipids, and structural fibers that build larger, more intricate cells. It also enables the development of new forms of motion. Some eukaryotes evolve flagella whip-like appendages that allow them to swim through the water rather than drift passively. Others form pseudopodia, extensions of their cytoplasm that reach out and engulf food. For the first time, life becomes mobile in the open ocean, capable of actively seeking resources rather than waiting for them to arrive. The ocean of this time is still dominated by bacteria and archaea, but the presence of eukaryotes begins to alter the balance. Their larger size means they sink faster when they die, carrying carbon to the seafloor, where it becomes trapped in sediments. This deep burial of organic matter removes carbon dioxide from the atmosphere and contributes to further oxygenation. The Earth's air grows clearer as biological complexity increases, a feedback loop that rewards evolution with stability. The byproducts of metabolism shape the planet's climate, and the planet's chemistry shapes the course of life. Under the microscope of imagination, the world of the mid-Proterozoic would appear quiet yet intricate. Microscopic algae drift through the upper layers of the sea, their green and brown pigments capturing light that penetrates the water. Protozoa glide among them, feeding on smaller cells, while others float in chains or clusters, forming colonies that shimmer faintly as they turn. These communities form the first planktonic ecosystems invisible to any eye, yet vital to the balance of gases in the atmosphere. Every breath of oxygen we know today has its origin in such uncountable cells performing photosynthesis beneath the ancient sun. The evolution of eukaryotes also transforms the flow of nutrients. Their internal membranes and organelles allow them to process metals and minerals in new ways, influencing the chemical composition of the ocean. Elements like iron, zinc, and molybdenum, once free in solution, become incorporated into enzymes and proteins. The sea becomes a reservoir of biological chemistry, its properties defined not only by physics, but by the metabolic needs of life. The line between geology and biology blurs as minerals become biological tools and organisms alter mineral cycles in return. The ocean is no longer just a setting for life, it becomes life's product. Eukaryotes diversify into many forms, some single-celled, others beginning to cooperate in loose colonies. The line between individual and group begins to blur. Some cells remain attached after division, forming filaments that sway gently with currents. Others create hollow spheres that trap nutrients inside. These early associations are precursors to multicellularity, though at this stage they are simple and fragile. Yet they demonstrate that cooperation can provide stability and resilience in an unpredictable world. When conditions change, the colony can survive even if some cells perish. When nutrients are scarce, shared, resources sustain the group. The principle of unity, many cells acting as one, has entered evolution, and with it the potential for bodies. In the shallows where light and nutrients meet, these communities flourish. The water glows green and gold, filled with suspended life that refracts sunlight into shifting colors. At night, when the surface cools, some of these organisms drift downward into darker water, carrying oxygen and organic matter into the depths. There they become food for other microbes, linking surface photosynthesis with deep-sea respiration. The ocean begins to behave as a single integrated system, its chemistry cycling through life and back into the environment with remarkable efficiency. At the same time, the development of eukaryotic cells introduces genetic innovation on an unprecedented scale. Sexual reproduction, though primitive, emerges as a mechanism for mixing genetic material between individuals. Instead of dividing identically, some cells exchange nuclei or fuse entirely before splitting again. This exchange creates diversity, accelerating evolution. Mutations that once accumulated slowly now combine and recombine, producing endless variation. Evolution gains speed and with it adaptability. Life can now respond to change not only by enduring but by experimenting. The environment continues to test this adaptability. Periods of glaciation recur, interspersed with long intervals of warmth. The oceans alternately contract and expand, altering salinity and nutrient supply. Eukaryotic organisms evolve strategies for survival, resting cysts that endure freezing-resistant spores that drift through time until favorable conditions return. Each crisis strengthens the resilience of life's new architecture. By the end of these cycles, eukaryotic cells dominate the visible biosphere, forming mats colonies and planktonic layers that stretch across the seas. The microbial world of the earlier Earth has given birth to complexity. Deep within some colonies, a few cells begin to specialize. Outer layers protect those within, while inner cells handle metabolism or reproduction. This primitive division of labor foreshadows the organization of tissues and organs that will appear much later. The concept of individuality begins to dissolve as cooperation proves more successful than isolation. Evolution driven by chemistry and circumstance is discovering the architecture of multicellular life. The fossil record of this era is sparse, but traces remain microfossils with complex walls, impressions of filaments and molecular remnants preserved in ancient shales. They reveal a quiet revolution, the emergence of cells with nuclei, the formation of partnerships within cells, and the first stirrings of coordinated growth. Each of these steps builds on the foundation laid by billions of years of microbial evolution and planetary transformation. By the close of this chapter in time, the oceans are no longer solely bacterial realms. They are worlds of drifting complexity illuminated by sunlight and sustained by oxygen. The eukaryotic cell, with its internal structures and shared ancestry, becomes the standard unit of life. From this single innovation cooperation between once separate beings will descend every animal, plant and fungus that follows. The planet, stabilized by oxygen and shaped by motion, has created within itself a new level of order. The Earth breathes more deeply now its oceans alive with potential, its chemistry tuned to support evolution's next great experiment, the creation of many from one. With the rise of eukaryotic life, the Proterozoic world enters an age of subtle abundance. The seas are no longer dominated by solitary microbes drifting in chemical gradients, but by vast diverse communities of cells that cooperate, cluster, and build new forms. Though invisible to the naked eye, their combined presence transforms the planet. Oxygen levels continue to climb as photosynthetic eukaryotes join cyanobacteria in enriching the atmosphere. The ocean, once a realm of chemical reactions, becomes an immense living fabric, its layers teeming with microscopic complexity. In this new environment, multicellularity begins to emerge not as a sudden leap, but as an accumulation of advantages, the result of millions of small decisions made by single cells over deep time. Each step toward cooperation brings greater efficiency, protection, and endurance, allowing colonies to survive the shifting conditions of a restless planet. In the upper layers of the sea, where sunlight penetrates through the blue water, colonies of simple multicellular algae drift with the currents. Their cells form filaments, sheets, and hollow spheres bound together by thin membranes of organic gel. The coordination among these cells is primitive but effective. Some focus on capturing light, others on nutrient storage or reproduction. This early division of labor marks the beginning of specialization. As colonies grow, they produce shadows beneath them that alter the flow of light and heat, subtly changing the local environment. Life is now shaping its own surroundings not through individual power, but through collective presence. These quiet multitudes do not move quickly or act with intent, yet their combined influence reaches across oceans. The chemistry of the planet adjusts in response. As photosynthetic life expands, oxygen continues to enter the atmosphere, oxidizing surface minerals and feeding the ozone layer high above. The increase in ozone shields the planet from ultraviolet radiation, making the upper layers of the ocean safer for life. With each generation, cells evolve to tolerate more oxygen and to use it more efficiently. Respiration becomes more widespread, linking the cycles of carbon and energy in a way that binds all ecosystems together. The once fragile balance between oxygen production and consumption now stabilizes, maintained by the vast biological machinery of the seas. Beneath the surface, darker waters remain home to ancient lineages of bacteria and archaea that persist in oxygen-poor zones. They form mats and films on the seafloor, feeding on sulfur and methane, as they have for billions of years. These communities continue to recycle elements between living and non-living matter, ensuring that the deep earth and surface remain connected. The oxygen from above diffuses slowly downward, reaching only a few hundred meters before vanishing into the chemical reactions below. This vertical division between oxygenated and anoxic layers remains a defining feature of the Proterozoic ocean. It shapes where multicellular life can evolve and where it cannot, guiding the geography of evolution itself. The growth of multicellular colonies accelerates sediment formation. As these organisms die, their remains settle gently through the water, creating thin organic layers that blanket the seafloor. Over millions of years, these sediments become the foundation of black shales, rich in carbon. The burial of this carbon draws down carbon dioxide from the atmosphere, allowing oxygen levels to rise even further. The Earth, through the quiet work of its smallest inhabitants, continues to refine its own air. The exchange between living and dead matter now regulates global chemistry in a self-sustaining cycle. The biosphere has become a planetary engine. In coastal shallows where waves stir nutrients from the land, multicellular algae grow in dense mats that ripple with the tides. These structures, neither plant nor animal, form the first visible vegetation of Earth. Their surfaces glisten in sunlight, and when tides recede, they leave behind textures of organic film and trapped sediment that fossilize easily. Each layer of these mats records a moment in the history of collaboration cells, linked together, sharing nutrients, responding to light as a unit, rather than as individuals. Over generations, these colonies become more complex, experimenting with new geometries and patterns of growth. Some branch outward into filamentous forms, others thicken into cushions anchored by holdfasts that grip the substrate. Life is learning to shape its body. The proliferation of oxygen-producing organisms transforms the color of the world. The green of photosynthetic pigments becomes the dominant hue of the ocean surface, reflecting the growing influence of life. Sunlight scattered from above now interacts with biological color rather than mineral reflection. The seas glow faintly turquoise under the Proterozoic sky, an optical signature of a living planet. The oxygen they release rises into the atmosphere, diffusing outward and reacting with gases from volcanoes. The delicate equilibrium between air and sea stabilizes climate-moderating temperature extremes and allowing liquid water to persist across vast stretches of time. As multicellular life spreads, it begins to occupy new ecological roles. Some colonies evolve feeding mechanisms engulfing smaller cells for sustenance, rather than relying solely on photosynthesis. Others become more efficient at capturing sunlight through flat, broad surfaces that increase their exposure to light. These different strategies create the first food webs chains of energy exchange that link producers and consumers. The ocean now supports a variety of trophic levels, though all remain microscopic. Life has diversified in form and function, establishing the ecological architecture that will later scale upward into visible complexity. The continents worn by weathering continue to release minerals that nourish these organisms. Rivers deliver a steady supply of phosphorus and other nutrients into the sea, where they are taken up by photosynthetic life and later buried in sediments. This flow of materials between land and ocean acts as a conveyor of fertility, ensuring that even as one generation of organisms dies, another can flourish. The balance of erosion, productivity, and burial becomes the heartbeat of the biosphere. Every drop of rain, every grain of dust plays its part in sustaining the quiet abundance of the oceans. In the deep geological record, the traces of this era are delicate but unmistakable. Layers of black shale enriched in organic carbon mark the proliferation of life. Thin bands of carbonate indicate intervals of stability and oxygenation. Microfossils preserved in chert and shale reveal intricate cell walls, complex ornamentation, and evidence of multicellular organization. They show that life, though still confined to the sea, had achieved extraordinary sophistication. The cells of this age possess nuclei, mitochondria, and internal membranes, the hallmarks of advanced biochemistry. They are the ancestors of every creature that will follow. Above the planet, the ozone layer thickens, filtering ultraviolet radiation and allowing the surface waters to remain stable for longer periods. The climate influenced by continental drift and ocean circulation oscillates, but rarely veers into extremes. The Earth has entered a long calm, a billion-year interval, sometimes called the boring billion, not because nothing happens, but because change occurs so steadily that catastrophe is absent. This stability allows evolution to refine complexity quietly. In the gentle constancy of light and water, the seeds of all future diversity mature in silence. By the end of this stage, the oceans are rich with invisible gardens of multicellular life. They sway with currents, bloom in the warmth of sunlight, and vanish into the depths as they die. The continents once barren reflect their influence in red and grey sediments born of oxygen and life. The air above holds steady, carrying enough oxygen to support metabolism far beyond the microscopic. The world is poised on the threshold of visible life, yet it remains tranquil, governed by the rhythm of tides and time. The quiet multitudes that fill the Proterozoic seas prepare the planet for what comes next. The awakening of complexity that will one day turn the silent ocean into a theatre of motion and form. As the quiet seas fill with multicellular life, the solid body of the Earth shifts again. Through the slow rhythm of plate motion, the continents that once drifted apart begin to gather, converging into a single supercontinent known as Rodinia. Its formation is gradual, a process spanning hundreds of millions of years as fragments of crust collide, weld together, and rise above the waves. Mountain chains form along the sutures where plates meet, while vast basins open elsewhere to receive the runoff of erosion. When Rodinia finally dominates the globe, it stretches from pole to pole, a massive irregular landmass surrounded by a global ocean. Its coasts face a single immense sea, and its interior lies far from moisture, covered in arid plains and ancient shields of exposed rock. Though barren and lifeless to the eye, this union of continents transforms everything about the planet, from the pattern of winds and currents to the balance of heat and climate. The assembly of Rodinia marks one of the great reorganizations of the Earth system. With so much land gathered together, the planet's reflectivity changes. Sunlight bounces from deserts and highlands, cooling the atmosphere. Meanwhile, rainfall diminishes over the supercontinent's interior, slowing chemical weathering and reducing the drawdown of carbon dioxide from the air. Carbon dioxide levels rise as volcanic emissions continue balancing the global temperature and preventing total glaciation. The Earth hovers in a steady state, neither frozen nor overheated, a long equilibrium that lasts for nearly 1 billion years. The oceans that encircle Rodinia circulate in immense gyres, driven by trade winds and polar currents. These slow-moving waters distribute heat unevenly, warming some regions while others cool. In these contrasts, the diversity of marine environments grows. The planet, though dominated by one continent, becomes more ecologically varied than ever before. Along the margins of Rodinia, life flourishes. Shallow continental shelves provide broad zones of sunlight and nutrients, where multicellular algae and microbial mats thrive. Stromatolite reefs grow in abundance, creating thick carbonate platforms that record stable conditions. The oceans above them shimmer with green and golden hues as photosynthetic organisms bloom in seasonal rhythms. Oxygen released by these organisms accumulates not only in the atmosphere, but also within the ocean itself, creating deeper oxygenated layers. For the first time, oxygen begins to reach the seafloor in certain regions, transforming the chemistry of sediments and paving the way for more complex forms of life to emerge. The planet, shaped by the slow tectonic pulse of its crust, becomes increasingly hospitable to its microscopic inhabitants. In the interior of Rodinia, erosion continues its patient work. Rivers few and intermittent carve valleys that lead to evaporating lakes and inland basins. Winds sweep across these dry plains, lifting dust into the air and carrying it to the coasts. There the dust settles into the sea, enriching coastal waters with minerals and trace elements. Even far from the ocean, the land participates in the cycles of life. Weathering releases nutrients that eventually find their way back to the sea, sustaining productivity over geological time. In this way, Rodinia's enormous size does not stifle life, but feeds it indirectly through the slow recycling of its rocks. The supercontinent also influences the composition of the atmosphere. Volcanic belts along its edges release carbon dioxide, sulfur dioxide, and water vapor. These gases interact with oxygen, forming aerosols that affect the climate and color of the sky. Sunsets glow redder, and the air takes on a faint haze in some regions. The greenhouse gases maintain a temperate climate despite the reduced efficiency of weathering on the land. The long-term stability of temperature across Rodinia's reign is remarkable, a near balance between volcanic outgassing and biological carbon burial. This equilibrium supports the persistence of the oxygenated atmosphere, ensuring that evolution proceeds in steady increments rather than catastrophic swings. Within the oceans, diversity deepens. Simple multicellular algae diversify into many lineages, each adapted to specific depths, light conditions, and chemical niches. Some develop mineralized cell walls using calcium carbonate or silica to strengthen their structures. These innovations allow them to resist predation by single-celled grazers and to maintain their shape in turbulent water. The first delicate shells appear, though still microscopic, hinting at the future architecture of marine life. Eukaryotic plankton spread across the seas, forming the base of increasingly intricate ecosystems. Each wave, each current carries uncountable cells that together regulate the flow of energy through the planet. The quiet multitudes of the earlier oceans have evolved into a symphony of interdependent species, each performing a small part in the global cycle. Rodinia's geography influences climate patterns that shape these ecosystems. Monsoon-like systems develop where warm oceans meet the edges of the continent, bringing periodic rains that erode coastal highlands. These rains carry sediments into shallow seas, creating deltas rich in nutrients. Their algal blooms pulse, seasonally drawing carbon from the atmosphere and releasing bursts of oxygen. When these organisms die, they sink to the seafloor and decompose, locking away organic carbon. The cycle strengthens the oxygen reservoir of the air, maintaining the planet's redox balance. Over time, sediments from these blooms form thick deposits of carbonate and shale, creating vast geological records of Rodinia's long stability. In deeper waters, anoxia persists. Beneath the oxygenated layers, the old chemistry of the Earth continues. Sulfate-reducing bacteria still dominate in the dark, producing hydrogen sulfide that reacts with iron to form pyrite. These processes create subtle chemical boundaries that ripple through the water column, influencing where life can exist. The interaction between oxygenated and anoxic zones becomes a defining feature of the mid-Proterozoic ocean. Each boundary acts as a frontier of evolution, challenging organisms to adapt to fluctuating chemistry. The resulting diversity of metabolic strategies ensures that the biosphere remains flexible, capable of enduring future upheavals. Over millions of years, Rodinia's mountains wear down their peaks, reduced to low hills and plains. Sediments derived from their erosion accumulate along continental margins, burying organic material that fuels further oxygen rise. The planet's crust grows thicker and stronger, forming the stable cratons that will survive into the present day. The magnetic field remains steady, shielding the atmosphere from solar wind and preserving its composition. Beneath this shield, the long calm of the Proterozoic continues, providing a stage for slow, evolutionary innovation. From space, the planet during Rodinia's reign would appear serene. A vast continent of ochre and brown stretches across much of one hemisphere, surrounded by blue oceans streaked with white cloud bands. Ice caps glint faintly at the poles, but the majority of the world lies under temperate skies. The rhythm of the seasons is mild, the storms predictable, the tides steady. It is a world in balance, a planet that has learned to regulate itself through the interplay of rock, air, and life. Though no creatures yet walk its surface or swim with intent in its seas, the foundations of their future are securely in place. As the long age of Rodinia endures, time itself seems to slow. Evolution continues in microscopic increments, refining cells, refining metabolism, and experimenting with form. The oxygen-rich atmosphere thickens the ozone layer, ensuring stability. Carbon cycles smoothly between land, sea, and air. The quiet continents drift only slightly, and life freed from the tyranny of catastrophe continues its subtle ascent. The Proterozoic world has entered its grand equilibrium, a billion years of peace, in which the planet's internal energy, its oceans, and its living chemistry reach a state of near harmony. Yet within that stillness, deep beneath the surface, forces are already gathering. The same tectonic restlessness that built Rodinia will one day tear it apart, ushering in a new era of change. But for now, under a pale sun and blue sky, the world rests within the calm dominion of Rodinia, a planet at peace with itself. The long calm of Rodinia does not last forever. Deep within the mantle, heat accumulates beneath the thick crust of the supercontinent, and convection currents press upward with slow insistence. Over millions of years, the stress builds along hidden seams until the surface begins to crack. Volcanoes erupt through the fractures, pouring basalt across the land and releasing clouds of gas into the atmosphere. Rivers of lava harden into dark plateaus that shimmer faintly under the Proterozoic sun. As the crust thins, rift valleys form, filling with shallow seas, where continental blocks begin to drift apart. The breakup of Rodinia has begun, and with it comes the reorganization of the planet's oceans, climates, and biospheres. The process unfolds not in violence but in immense slowness, measured by the pace of continents creeping apart a few centimeters each year, yet relentless. Over tens of millions of years, these small movements reshape the face of the Earth. As the supercontinent fractures, new coastlines appear. Ocean water invades the rift valleys, creating long, narrow gulfs lined with volcanic rock. The meeting of seawater and magma produces chemical reactions that release metals and gases, enriching the water with iron, sulfur, and carbon dioxide. These nutrients feed microbial and algal life-sparking blooms that turn the shallows green. The newly opened seas become cradles of productivity, where photosynthetic organisms thrive in the interplay of light and minerals. The oxygen they release continues to flow into the atmosphere, maintaining the balance established during Rodinia's long reign. Yet the gases emitted by volcanic eruptions, carbon dioxide and methane, thicken the air, warming the planet. For a time the world grows humid and tropical with rainfall, washing nutrients from the rising rift shoulders into the ocean basins below. The fragmentation of Rodinia also changes the pattern of ocean circulation. Currents that once circled the vast supercontinent now weave among separate land masses, creating new gyres and upwellings. These movements redistribute heat across the planet, ending the long stability that had prevailed for hundreds of millions of years. Regions that were once arid now receive moisture. Others once temperate begin to cool. The redistribution of nutrients in the sea stimulates new ecological patterns. Eukaryotic algae and early multicellular organisms adapt to the varied conditions, diversifying into distinct lineages suited to shallow lagoons, open waters, and continental slopes. The biosphere responds to tectonic motion with an outpouring of variety. Meanwhile, the breakup of the supercontinent intensifies weathering. The fresh basalt exposed along rift zones reacts with rainwater and carbon dioxide, drawing greenhouse gases out of the atmosphere and cooling the climate. Over time, this process may contribute to one of the most severe glaciations in Earth's history. Ice begins to form again at the poles, advancing across the continents as temperatures fall. Snow accumulates on high plateaus, reflecting sunlight and amplifying the chill. The planet, once warmed by the volcanism of rifting, begins to slip toward global cold. In some intervals, glaciers extend nearly to the equator, marking the beginning of another snowball Earth state. The alternation between volcanic warming and weathering-induced cooling becomes one of the dominant rhythms of the late Proterozoic climate. Within the oceans, these changes in temperature and chemistry reshape the distribution of life. As glaciers advance, sea levels drop, exposing broad shelves and isolating shallow basins. Many coastal ecosystems collapse, but in their place new habitats form along the ice margins and in the remaining equatorial waters. The survivors adapt to fluctuating salinity, temperature, and nutrient supply. Among them are lineages of simple multicellular algae and proto-animals that experiment with new forms of organization. These early organisms learn to endure instability through flexibility, a quality that will define life's response to environmental change in all future ages. The disintegration of Rodinia is not uniform. Some fragments remain attached for tens of millions of years, forming subcontinents connected by narrow isthmuses. Others drift freely, separated by widening oceans. Each piece becomes its own world with distinct climates, currents, and ecosystems. The configuration of land and sea constantly evolves, shaping wind patterns and rainfall distribution. The young oceans that form between the fragments known to geologists as the Iapetus and the Panthallassic basins become centers of geochemical exchange, where hydrothermal activity along new ridges releases minerals that nourish the biosphere. The interplay between spreading ridges and subduction zones drives a new cycle of tectonic renewal. Volcanism remains intense throughout this period, and its effects on the atmosphere are complex. The carbon dioxide emitted by eruptions counteracts the cooling from weathering, preventing the planet from freezing completely. When ice advances, volcanic gases accumulate under the ice sheets, creating a greenhouse that eventually melts them. This push and pull between volcanic warmth and glacial cold defines the end of the Proterozoic. It is a period of oscillation, with the planet swinging between extremes, yet maintaining overall stability. Each fluctuation resets the chemical balance of the oceans, redistributing nutrients and oxygen. Life, though, stressed benefits from these cycles, evolving new strategies to exploit the shifting conditions. The continents themselves bear the scars of their separation. Great faults run across the land, marking where the crust has torn apart. Mountain ranges that once rose along collision zones are eroded into rolling plains, their sediments carried into the sea to form new deposits. The crust thickens and stabilizes in some regions while thinning in others, producing variations in elevation that influence climate and ocean circulation. Rivers follow the paths of least resistance, carving valleys that lead to expanding coastlines. With every rainfall, the landscape of Rodinea's fragments softens its sharp edges, worn into curves by time. In the midst of geological upheaval, life continues its slow advance toward complexity. Some eukaryotic organisms begin to exhibit true multicellularity, forming bodies with tissues and coordinated growth. Fossils from this time show branching filaments and sheet-like forms, perhaps the ancestors of simple seaweeds. Others appear as microscopic clusters with distinct cell types, precursors to the first animals. These innovations arise in response to the dynamic environment created by the breakup of Rodinia. Where stability once favored endurance, change now rewards flexibility and cooperation. The biosphere becomes a laboratory of experimentation guided by chemistry, climate, and chance. The breakup of the supercontinent also affects the balance of oxygen in the air. The burial of organic carbon in new sediments allows oxygen levels to rise once more, reaching perhaps 1/10 of modern values. This enrichment supports the metabolism of larger organisms and encourages the spread of aerobic life into new ecological niches. The atmosphere, now sufficiently oxidized, develops a stable ozone layer that protects surface waters from ultraviolet radiation. The planet's surface becomes increasingly habitable, even as its geology remains in flux. From orbit, the Earth at this time would appear transformed. The single continental mass of Rodinia has fractured into multiple landmasses scattered across a global ocean. Between them, chains of volcanoes trace the outlines of new tectonic boundaries, glowing faintly through the haze of volcanic gases. Ice gleams at high latitudes and clouds swirl around tropical seas alive with microscopic life. The colours of the planet, deep blue, white, green and ochre, reflect a new balance of land, water and air. The world is no longer static. It is dynamic, rhythmic, self-renewing. By the end of this great rearrangement, the continents have taken on configurations that anticipate the next chapter of Earth's story. The planet has passed through cycles of assembly and disassembly, learning, resilience through motion. The breaking of Rodinia resets the climate, rejuvenates the oceans, and stirs evolution toward new thresholds of complexity. The long stillness of the Proterozoic gives way to a world in transition, its stability replaced by restless potential. Beneath calm skies, the stage is set for the final transformations that will carry the Earth into its most remarkable age, the rise of animals and the dawn of the modern biosphere. As the fragments of Rodinia drift apart, the balance of heat and cold that has governed the Proterozoic world begins to tilt. The continents now scattered near the equator expose vast expanses of silicate rock to warm rain and sunlight. Weathering accelerates, pulling carbon dioxide out of the air and weakening the greenhouse effect that has long kept the planet temperate. The sun, still fainter than it will be in later ages, provides less warmth than the cooling atmosphere can retain. Temperatures fall slowly but steadily, glaciers form on mountain peaks, and the polar ice caps begin to creep toward lower latitudes. Over millions of years, the process gains momentum as ice reflects sunlight back into space, and cooling feeds upon itself. The Earth enters one of its most extreme transformations, the snowball Earth phase, where nearly the entire surface may have frozen beneath kilometers of ice. From space, the planet would appear dazzling white, its oceans sealed under a shell of frozen water, its continents hidden beneath snow and reflective frost. The atmosphere thins and dries, clouds diminish, and the contrast between day and night becomes stark. The oceans, though imprisoned beneath the ice, remain liquid in their depths, warmed by geothermal heat and by the faint movement of deep currents. Within these dark waters, life endures confined to thin layers near hydrothermal vents or beneath cracks in the ice where light still filters through. Photosynthetic organisms survive in refuges where meltwater opens small polynyas near volcanoes or regions of upwelling, while chemosynthetic microbes continue their work around hot springs on the ocean floor. The biosphere contracts but does not vanish. Its persistence during these global freezes marks one of the great tests of resilience in the history of life. On the continents, glaciers grind across the land, erasing ancient mountains and leaving behind striated bedrock. Ice sheets several kilometers thick move slowly but with unstoppable weight, scouring valleys and crushing rock into fine powder. The grinding releases minerals that accumulate at the base of the ice, waiting for the time when meltwater will carry them to the sea. The land is silent, devoid of liquid water, its surface locked in a cold stasis that will last millions of years. Volcanic eruptions punctuate the stillness, their plumes rising through the frozen atmosphere and spreading ash over the white landscape. The dark particles absorb sunlight, creating faint grey streaks on the ice. Each eruption releases carbon dioxide into the air, but for a long time the gas remains too diluted to counter the planet's albedo. Beneath the ice, chemical changes continue unseen. In the absence of weathering, the carbon dioxide emitted by volcanoes accumulates slowly in the atmosphere. With oceans frozen, there is little exchange of gases between sea and sky, and carbon cannot easily return to rock through the usual cycles. For millions of years, volcanic outgassing continues unchecked. Layer by layer, the invisible greenhouse thickens until the balance tips. When atmospheric carbon dioxide reaches a critical threshold, the air traps enough heat to begin melting the ice. The thaw starts near the equator, where sunlight is strongest and spreads rapidly once bare rock and water appear. Dark surfaces absorb heat, amplifying the effect. Within a few thousand years, a moment in geological time, the global ice sheets retreat. Torrents of meltwater pour across the continents, carrying vast quantities of eroded debris into the ocean. The frozen world transforms suddenly into one of flood and turbulence. The return of liquid water triggers violent chemical reactions. The influx of nutrients from melting glaciers fertilizes the oceans, sparking massive blooms of photosynthetic organisms. Oxygen production surges and the air fills again with the breath of life. As these organisms die and sink, they trap carbon in sediments, stabilizing the climate once more. The warming, however, overshoots for a time. With so much carbon dioxide accumulated during the freeze, the planet enters a brief greenhouse phase. Rain falls in torrents, weathering accelerates, and temperatures gradually return to equilibrium. The alternation between total freeze and intense warmth leaves distinctive layers in the geological record, glacial deposits overlain by thick carbonates known as cap dolostones, formed in the aftermath of melting. Each layer is a signature of catastrophe and renewal, a record of the planet's ability to swing between extremes and recover. These global glaciations, which occur more than once in the late Proterozoic, reshape the chemistry of the oceans and the path of evolution. The prolonged isolation of life under ice fosters new adaptations. Organisms evolve mechanisms to withstand cold darkness and scarcity. Some develop protective coatings, others learn to form dormant spores or cysts that can wait for centuries until conditions improve. When the ice retreats, these survivors proliferate rapidly in the nutrient-rich seas, diversifying in an explosion of forms. The stress of near extinction becomes a creative force driving evolution toward greater complexity. In the aftermath of each snowball episode, the diversity of eukaryotic organisms increases and new multicellular lineages appear. The melting ice also releases the minerals ground from the continents, increasing the concentration of phosphorus and trace metals in the sea. These nutrients support the growth of larger and more organized organisms, including early multicellular, algae, and proto-animals. The oxygenation that follows the glaciations deepens, reaching levels close to those that will later sustain animals. The biosphere, once confined to narrow refuges, expands again across the oceans. Every freeze-thaw cycle thus resets the planet, erasing some lineages, but preparing the way for others. The climatic oscillations of this period are among the most dramatic the planet will ever experience. The alternation between snowball and greenhouse states transforms the landscape repeatedly, ensuring that no environment remains constant for long. This instability paradoxically produces resilience. Life becomes more adaptable, more capable of enduring change. By the end of the final glaciation around 650 million years ago, the Earth emerges from its icy prison into a world of mild climates and enriched oceans. The air carries more oxygen than ever before, and the continents newly exposed are covered in sediments that record the story of ice and fire. The sky above this reborn world is a paler blue washed clean by centuries of condensation and frost. Clouds drift over green-tinged seas filled with planktonic life. Along the coasts, microbial mats reappear, joined now by colonies of simple multicellular organisms that form sheets and filaments upon the shallow seabed. The Earth breathes again, warmer and more vibrant than before, its systems reset and ready for further transformation. The Snowball Earth episodes mark not the end of habitability, but the refining of it, as though the planet itself had tested the limits of endurance and found them wide. By the close of this chapter, the world has changed beyond recognition. The continents lie scattered across the equator, the atmosphere stable yet dynamic, the oceans alive with oxygen and nutrients. The scars of glaciation remain in polished stones and layered sediments, reminders of a time when the entire planet nearly froze. Yet it is from this ordeal that the stage is set for the next great leap. The Earth, forged by cycles of stability and collapse, now holds within its oceans all the conditions necessary for the rise of complex life. Beneath calm waters and bright skies, the seeds of animals wait ready to awaken in the dawn that follows the last ice. When the last of the great Proterozoic glaciers retreat, the world stands transformed. The continents, freed from the weight of ice, rise slowly through isostatic rebound, their coastlines reshaped by meltwater and erosion. Rivers rush down from the highlands, carrying minerals into the newly warmed seas. The oceans, stirred by fresh circulation and enriched by sediment, become fertile like never before. Light once again penetrates deeply into the water, feeding layers of photosynthetic life that expand across the planet. Oxygen levels climb to new heights, approaching a threshold that will permit the rise of animals. After nearly 2 billion years of microbial dominance, the Earth begins to hum with a new kind of potential. The aftermath of the Snowball Earth episodes brings a climate of remarkable stability. The planet, having endured extremes of cold and heat, now finds balance in a temperate middle ground. Carbon dioxide, once dangerously high, is drawn down by vigorous weathering and by the expansion of life that captures it through photosynthesis. Volcanic activity continues to feed trace gases into the atmosphere, but the greenhouse effect now operates within narrow limits. Rain falls in steady cycles, the oceans circulate more efficiently, and the continents rest in scattered configurations that prevent the formation of another global ice age. The Earth has emerged from its trials resilient and self-regulating, a world capable of sustaining intricate ecosystems. In these renewed oceans, life becomes visible in form and motion for the first time. Soft-bodied multicellular organisms begin to spread across the seafloor, forming mats and colonies that resemble carpets of flesh. Among them are the earliest known members of the Ediacaran biota, enigmatic creatures unlike anything alive today. Some appear as discs pressed into sediment, others as frond-like structures that rise a few centimeters above the mud. Their bodies are delicate and symmetrical, composed of networks of tissues that channel nutrients and gases without the need for organs. Many attach themselves to the substrate, absorbing dissolved matter directly from the water. Others lie partly buried, their shapes molded by currents. These organisms represent a new principle in biology, the organization of many cells into coordinated bodies that respond to the environment as one. The chemistry of the oceans supports this leap in structure. Oxygen dissolved in the water allows larger organisms to maintain metabolism across tissues, while nutrients released by glacial erosion provide the raw materials for growth. Calcium, phosphorus, and sulfate concentrations rise, enabling new biochemical pathways. Some organisms begin to secrete thin mineral coatings, perhaps to stabilize their forms or protect against the abrasive currents. These experiments with skeletons are primitive but revolutionary, hinting at the evolution of hard parts that will later define the fossil record. The seafloor becomes a patchwork of textures, soft microbial mats, gelatinous colonies, and the faint imprints of the first skeletal frameworks. As diversity increases, ecological complexity follows. Some organisms occupy the surface of the sediment using sunlight or filtering nutrients from the water, while others burrow shallowly below, disturbing the mud and allowing oxygen to penetrate deeper into it. This mixing of sediments marks the beginning of bioturbation, a process that will profoundly alter the chemistry of the seafloor. The circulation of oxygen and organic matter through the upper layers of sediment changes the availability of nutrients, influencing the evolution of all marine life. Ecosystems now consist not only of organisms but of the environments they continually reshape. The rise of multicellular life also transforms reproduction. Simple division gives way to the first recognizable cycles of growth and regeneration. Some organisms reproduce by releasing spores or fragments that drift in currents before settling elsewhere. Others alternate between stationary and free-floating stages, spreading across the ocean floor in slow expansion. These new strategies ensure resilience in changing environments, allowing species to colonize new habitats as continents drift and sea levels fluctuate. With each generation, the patterns of life become more intricate, bound together by energy, matter, and movement. In the shallows near coasts, algae and cyanobacteria continue to dominate, forming thick layers of photosynthetic biomass that pump oxygen into the air. Above them, the atmosphere grows more transparent, the ozone layer strengthening to shield life from ultraviolet radiation. The sky turns a paler blue and sunlight glitters on seas, alive with suspended life. This light becomes the energy that drives the next great evolutionary threshold, the appearance of coordinated movement. Within some multicellular lineages, groups of cells begin to contract rhythmically, generating motion. The first stirrings of muscles and nervous coordination arise, allowing simple gliding or undulating behavior. Life, once stationary, begins to move with purpose. The planet's surface records these changes in layers of rock and chemical traces. Black shales rich in organic matter alternate with lighter carbonates formed in oxygenated waters. Fossil impressions preserve the outlines of soft-bodied creatures pressed into ancient seabeds. Some show radial patterns, others bilateral symmetry, the first hints of the body plans that will dominate the animal kingdom. The atmosphere itself bears the marks of transformation. Stable oxygen levels near 1/5 of modern concentrations, balanced by volcanic gases and biological uptake. The air now supports fire, though no plants yet exist to feed it, and lightning storms flicker over the oceans, discharging energy into the gas-rich sky. The continents still drifting carry climates that range from humid equatorial coasts to icy polar shelves. The tides, stronger than today due to the moon's closer orbit, shape the rhythms of shallow ecosystems. Twice daily, vast areas of reef and microbial matter are exposed and submerged, creating alternating periods of stress and opportunity. Organisms adapt to these cycles by developing stronger adhesion, flexible tissues, and internal storage systems for water and nutrients. In these challenges lie the blueprints for the adaptability of later life. The Earth's environment never entirely still continues to instruct evolution through its shifting conditions. As oxygen levels reach their new plateau, energy becomes abundant enough to sustain larger and more active organisms. The stage is set for predation, the next great evolutionary innovation. Some creatures begin to feed on others, rather than on dissolved nutrients or sunlight, introducing competition and mobility into the biosphere. Traces of this shift appear in subtle changes to the fossil record tracks and burrows, disturbed sediments, and faint chemical signatures of selective feeding. Life is beginning to organize itself into food chains linking organisms through the exchange of energy and matter. With predation comes response speed armor and behavior. The arms race that will define the Phanerozoic world begins in these quiet Proterozoic seas. The planet itself responds to these transformations with continued balance. Carbon cycles through the air and water in stable proportions. Volcanic activity replenishes nutrients. Ocean circulation carries oxygen into the depths. For the first time, the Earth operates as an integrated system dominated not by geology alone, but by the metabolism of life. The atmosphere, the ocean, and the crust are locked together in feedback loops that sustain habitability. From this equilibrium, the biosphere draws the stability required for further complexity. By the close of the Proterozoic Eon, the Earth has become a fully mature planet. It has endured bombardment, molten chaos, suffocation, freezing, and fire. It has grown continents, eroded them, broken them apart, and rebuilt them. Its oceans has breathed in and out their chemistry, rewritten by the labor of countless microbes. Out of this long preparation emerges a stable world rich in oxygen and nutrients, with ecosystems ready to support complex multicellular animals. Beneath the tranquil surface of the sea, life has built the foundations of movement, sensation, and interaction. The darkness of prehistory begins to glow with the first traces of awareness. Soon in the next eon, the Cambrian dawn will flood these waters with shape and motion. But here at the end of the Proterozoic, the planet rests for a moment in perfect poise, its air steady, its seas alive, and its future written in the silence of the deep.